In the last year, the world of artificial intelligence has been dominated by a single seismic promise. A promise made by the creators of models like OpenAI's O1 and Anthropic's Claude 3.7 thinking. They call them reasoning models. And the name says it all. These aren't just language models anymore. They are supposed to be reasoning models. They don't just give you an answer, they show you their work, generating pages of complex, step-by-step thinking that looks, for all the world, like a human mind grappling with a difficult problem. It feels like a breakthrough, a genuine step towards artificial general intelligence. But what if it isn't? What if it's all just a trick? A sophisticated performance designed to convince us of an intelligence that isn't really there? What if what we're witnessing isn't the dawn of thinking machines, but simply the illusion of thinking? These are not just philosophical questions. They strike at the heart of the billions of dollars being invested and the very direction of AI development. And recently, a team of researchers at Apple published a paper that might just be the most sobering analysis of these so-called reasoning models to date. They didn't just poke at these models, they built a controlled laboratory to dissect their minds. And what they found is a scary warning for anyone who believes we're on the fast track to AGI. Today, we're going on a deep dive into that study. We're going to see how these frontier models hold up under real pressure, away from the curated demos and hype. We're going to put the illusion of thinking to the test. So, how do you test if an AI is truly reasoning? The standard approach is to throw a bunch of math and coding problems at it, like the AIME or Math 500 benchmarks. If it gets the final answer right, it gets a point. But the researchers behind the illusion of thinking argue this is a flawed approach. The problem is something called data contamination. These massive models have been trained on a huge portion of the internet, which includes, you guessed it, solutions to those very same benchmarks. The model might not be reasoning at all. It could just be remembering. It's like giving a student a final exam they've already seen the answer key for. You're not testing their problem-solving skills, you're testing their memory. To get around this, the researchers did something brilliant. They turned to classic, controllable puzzles. Puzzles like the Tower of Hanoi, Blocks World, or River Crossing. These aren't your typical math problems. They have a clear logical structure, but their complexity can be precisely and systematically increased. You can test a model on a Tower of Hanoi with 3 disks, then 5, then 10, then 15. The underlying logic is the same, but the number of steps required explodes exponentially. This creates a clean, uncontaminated environment. More importantly, it allows researchers to not just check the final answer, but to validate every single step of the model's thinking process. Here's how the paper itself frames their approach. Current evaluations suffer from data contamination and do not provide insights into the reasoning trace's structure and quality. In this work, we systematically investigate these gaps with the help of controllable puzzle environments that allow precise manipulation of complexity. This setup enables the analysis of not only final answers, but also the internal reasoning traces, offering insights into how LRMs think. That phrase, how LRMs think, is the key. By using these puzzles, the researchers created a transparent window into the AI's mind. For the first time, they could move past the final answer and watch the process itself unfold step by miserable step. What they discovered reveals a startlingly clear pattern, which they break down into 3 distinct performance regimes. It's like a 3-act play about the rise and fall of artificial reasoning. The first act is for low-complexity problems. Think of a Tower of Hanoi with just a few disks. It's a simple, straightforward task. And here, something surprising happens. The specialized, expensive, large reasoning models are actually worse than their standard, non-thinking counterparts. In the first regime, where problem complexity is low, we observe that non-thinking models are capable to obtain performance comparable to or even better than thinking models with more token-efficient inference. Better and more efficient. The researchers found that in these simple cases, the reasoning models tend to overthink. They'll find the correct answer early on, but then waste thousands of tokens exploring incorrect paths as if they're obliged to perform the act of thinking even when it's not needed. It's like asking a theoretical physicist to calculate 2 plus 2. They might be able to do it, but they'll fill a whiteboard with equations first. It's inefficient, and sometimes they even manage to talk themselves out of the right answer. But then comes the second act. This is the sweet spot. When the problems reach a medium level of complexity, the large reasoning models finally pull ahead. This is where the long chain of thought, the self-correction, the detailed internal monologue, all the features they're designed for start to pay off. In the second regime with medium complexity, the advantage of reasoning models capable of generating long chain of thought begin to manifest, and the performance gap between model pairs increases. This right here, this is the heart of the illusion. This is what the companies demo on stage. In this zone, the models look like they are genuinely thinking. They make mistakes, they explore dead ends, they backtrack, and then through what looks like a flash of insight, they find the correct path. It is deeply, deeply convincing. For a moment, you really believe you're watching a new form of intelligence at work. But then comes the third and final act, the collapse. When the complexity is pushed just a little bit further, something dramatic happens. It's not a gradual decline, it's a cliff. The performance of both the standard and the advanced reasoning models completely collapses to zero. All reasoning models exhibit a similar pattern, with accuracy progressively declines as problem complexity increases until reaching complete collapse beyond the model-specific complexity threshold. Zero accuracy. After a certain point, they can't solve the puzzles at all. The magic is gone. But it's how they failed that is the most revealing part of this entire study. It's not that they try their best and run out of time or memory. Something much stranger is going on under the hood. This brings us to what is, in my opinion, the single most damning finding in the entire paper. A discovery so counterintuitive it forces us to reevaluate everything we think we know about how these models work. Look at this graph. It shows how much reasoning effort the model uses, measured in the number of thinking tokens it generates as the puzzle complexity increases. At first, the trend is exactly what you'd expect. Harder problem, more thinking. The line goes up. But then it hits that critical point, the exact same point where their accuracy collapses, and the line starts to go down. Unquote, upon approaching a critical threshold, which closely corresponds to their accuracy collapse point, models counterintuitively begin to reduce their reasoning effort despite increasing problem difficulty. This behavior suggests a fundamental scaling limitation in the thinking capabilities of current reasoning models. Let that sink in. The problem gets harder, but the model thinks less. It has a massive token budget. It's allowed to think for tens of thousands of tokens, but it gives up. This isn't like a human running out of brain power. It's like a student facing a tough exam question, writing 2 sentences, and then just putting their pen down, even though they have 3 hours left. It's not a resource limitation. It's a fundamental breakdown in the process itself. It suggests the model recognizes a level of complexity it is simply not built to handle, and its programming, its very architecture, causes it to retreat. The reasoning mechanism shuts down. But the researchers pushed even further. They wanted to know why it shuts down. So they designed one final killer experiment. They decided to make it as easy as possible for the model. For the Tower of Hanoi puzzle, they didn't just ask it to solve the problem. They gave it the exact step-by-step recursive algorithm to solve it instead. A perfect, flawless set of instructions. All the AI had to do was execute the steps. It no longer needed to plan or reason about the solution. It just needed to follow the recipe. The result? Unquote, even when we provide the algorithm in the prompt so that the AI model only needs to execute the prescribed steps, performance does not improve, and the observed collapse still occurs at roughly the same point. This further highlights the limitations of reasoning models in verification and in following logical steps to solve a problem. No improvement, nothing. It failed at the exact same complexity level. This is an absolutely crucial distinction. It means the failure isn't in high-level planning, it's in low-level execution. These models, for all their sophistication, are not reliable logical engines. They cannot consistently follow a long sequence of simple formal instructions. The thinking they produce is a fragile, probabilistic performance, not a robust, deterministic computation. And the final piece of evidence cements this conclusion. The researchers noticed a strange discrepancy in the model's abilities across different puzzles. Unquote, note that this model also achieves near-perfect accuracy when solving the Tower of Hanoi with n equals 5. Note that this model also achieves near-perfect accuracy when solving the Tower of Hanoi with n equals 5, which requires 31 moves, while it fails to solve the river crossing puzzle when n equals 3, which has a solution of 11 moves. This likely suggests that examples of river crossing with n greater than 2 are scarce on the web, meaning models may not have frequently encountered or memorized such instances during training. Did you catch that? The model can flawlessly execute dozens, even over 100 moves for the Tower of Hanoi, a problem that is a cornerstone of every computer science curriculum and is all over the internet. But it fails after just a handful of moves on a moderately complex river crossing puzzle, a problem that is far less common online. This is the ghost in the machine revealed. The reasoning is not a general capability. It's an echo. It's a masterful act of pattern matching on a scale we've never seen before. It can replicate the patterns for problems that is seen frequently, but when faced with a truly novel, complex logical sequence, the facade crumbles. The thinking is not emergent, it's memorized. So where does this leave us? The findings from this paper resonate with a growing skepticism from some of the most respected minds in the field, like Yann LeCun, Meta's chief AI scientist. He's been saying this for years, and it's a message the hype cycle often ignores. To really understand the stakes, you have to hear it from him directly.
We are not going to get to human-level AI by just scaling up LLMs. This is just not going to happen, okay? There's no way, okay? Absolutely no way. And whatever you can hear from some of my more adventurous colleagues, it's not going to happen within the next 2 years. There's absolutely no way in hell to, pardon my French. The idea that we're going to have, a country of genius in the data center, that's complete BS, okay? There's absolutely no way. What we're going to have maybe is systems that are trained on sufficiently large amounts of data that any question that any reasonable person may ask will find an answer through those systems, and you would feel like you have a PhD sitting next to you, but it's not a PhD you have next to you. It's a system with a gigantic memory and retrieval ability, not a system that can invent solutions to new problems, which is really what a PhD is. Okay.
Not a system that can invent solutions to new problems. That's the punchline. LeCun is making the exact same point as a paper, but from a different angle. He's saying these systems are becoming incredibly vast databases of human knowledge with a natural language interface. They feel like a PhD because they've essentially read more books than any PhD ever could. But that's retrieval, not creation. It's memory, not reason. This is the fundamental problem. The massive investments being made, particularly by companies like Meta, are built on the promise of scaling up these systems. But as LeCun and the Illusion of Thinking paper both argue, you can't just scale your way to true intelligence. The illusion of thinking is powerful, but an illusion is all it is. These models are not on a clear path to becoming general intelligences. They are on a path to becoming better and better simulators of intelligence. And while that's an incredible engineering feat, it's not the same thing. Which leads us to the final unsettling question. If the most advanced AI models from the world's leading labs are just getting better at faking it, what does that mean for the grand pursuit of AGI? Are we actually building a true thinking machine, or are we just perfecting the world's most convincing puppet? Let me know what you think in the comments below. If this analysis gave you a new perspective on the future of AI, consider liking this video and subscribing for more deep dives into the technology that is shaping our world. Thanks for watching.